Good day everyone, we are from Group 4. Our project title is called Green Hydrogen Productions via Water Electrolysis.
This is our table of contents.
So first of all, let me start with the process overview of our project. Green hydrogen production through electrolysis is a sustainable method that splits water into hydrogen and oxygen using electrical energy. Electrolysis of water is a promising technology for producing hydrogen which can be used as a clean fuel in various applications such as transportation, industry and also for energy storage. Let me just go briefly on our process specification of our project. Our main product is hydrogen and its purity would be 99.99% and our plant capacity is 100,000 tons per year. And our process, as I mentioned earlier, would be electrolysis and our scope is module which will be used in Aspen Plus simulation. The number of stacks will be 1 and the number of cells per stack will be 12. The overall reaction is as stated here, water will be producing oxygen and also hydrogen and there will be reaction in both anode and cathode sides and our raw material is just water and its flow rate would be 92,486 kg per hour. Now let's discuss about the unit operation of our project. The green hydrogen production process starts with feed water being directed into heater to increase its temperature to the optimal level for electrolysis. The heated water then enters the electrolyzer where it undergoes electrolysis by splitting water into hydrogen and oxygen gases. The electrolyzer has two main components, the anode where the oxygen gases is produced and the cathode where the hydrogen gas is produced. The oxygen gas from the anode is directed to an anode separator to ensure its purity by removing residual water or impurities, after which the purified oxygen is stored in the O2 stack. Similarly, for the hydrogen gas from the cathode is directed into a cathode separator to ensure its purity and the purified hydrogen is then stored in the H2 stack. This process efficiently produces and stores high purity of hydrogen and also oxygen gases. The next slide will be about the advantages of the green hydrogen production process. The first one would be about sustainability and zero emissions. This process uses water as raw material and produces hydrogen and also oxygen with no greenhouse gas emissions, contributing to the goal of zero carbon emissions. The second one would be the renewable energy integration. When powered by renewable energy sources such as solar or wind, the electrolysis process can produce green hydrogen, further decreasing the carbon footprint and promoting the use of clean energy. The third one would be high purity of products. The process involves separators for both hydrogen and oxygen, ensuring high purity levels for both gases, which is crucial for various applications in the energy and industry sectors. The fourth one would be about the energy storage. Hydrogen produced through this process can be stored and used as an energy carrier, providing a solution for energy storage and addressing the intermittency of renewable energy sources.
Now I will briefly explain about our block flow diagram and process flow diagram regarding our green hydrogen production. This is our block flow diagram BFD. Mainly water will be fed into the heater to heat up the water until 75 degrees Celsius for the whole process, and water is fed into the electrolyzer with 75 degrees Celsius with 7 bar. The mass flow rate of the water is fed into heater until 92,486 kg per hour. Since only water will be fed into the process, hence the total mass flow rate for inlet will be same as the water feed flow rate, that is 92,486 kg per hour. So after water is heat and fed into the electrolyzer, electrolysis process occur in the electrolyzer and splitting the oxygen gas at anode and hydrogen at cathode. Then the separator from both anode and cathode will separate and recycle again the impurities until only pure oxygen and hydrogen gas come out. The total mass flow rate that oxygen had come out from separator from anode was 82,137 kg per hour after we ran the Aspen Plus module, whereby the hydrogen gas come from cathode with separator had a mass flow rate of 10,349 kg per hour. The total mass flow rate out was the sum of the mass flow rate of oxygen gas and hydrogen gas, and after sum is similar and same with the total mass flow rate in. So is can conclude that mass flow rate in equals to mass flow rate out. This is our process flow diagram PFD, which is different from BFD. As you can see in PFD, we had add a control valve before the pump to control the flow rate of water, and we had added the pump P101 before we feed the water into the heater to increase its pressure from 1 bar to 5 bar. The mass balance energy balance table will be zoomed in for the next slide. As you can see here, this is our process flow diagram table. All the streams is listed down here with the each component's mass flow rate and total mass flow rate, volumetric flow rate, enthalpy, temperature, pressure, and so on. Actually, you can see here the enthalpy from stream 1 until stream 3, which we feed the water only before we going into the electrolyzer. Mainly will be the negative value, which indicates the exothermic reaction because the phase of the water is still in liquid. After we feed the water into the electrolyzer, the reaction become endothermic reaction, which the enthalpy become positive value as you can see in here, and then the oxygen and hydrogen produced is in vapor phase. So we mainly focus on hydrogen. The hydrogen produced from 92,486 kilogram per hour of the water will produce 100,001.24 tons per year of the hydrogen gas. So actually it depends on the water flow rate from the hydrogen gas produced. So in although it's on already exceed 1 tons per year, but we can adjust the mass flow rate like scale up or scaling down the mass flow rate of water.
So now I will present for the material properties for water, hydrogen and oxygen. So the first one is water, which is the chemical formula is H2O. The molar mass is 18.0 gram per mole. The density is 0.9167 gram per mole for solid. And for liquid is 0.99 gram per mole at 0 degrees Celsius. So the boiling point is 99.98 Celsius and the melting point is 0.00 Celsius. So at the right, you can see the MSDS for the water. Next, for hydrogen, the chemical formula is H2. The molar mass 2.0158 gram per mole and the density is 0.00082 gram centimeter cube. The boiling point is negative 252.87 Celsius and the melting point is negative 259.16 Celsius. So the MSDS also at the right. Lastly, for oxygen, chemical formula is O2. The molar mass is 2.01 gram per mole. The critical point is 118.9 Celsius. The density is 1.429 gram per liter. And the boiling point is negative 182.97 Celsius. The melting point is negative 218.76 Celsius. So, for the MSDS, you can refer the QR at the right side.
Now I will be explaining about the main process and reactions related to water electrolysis. The major unit in our process is called electrolyzer. An electrolyzer, when scaled up for green hydrogen production in high yield, is a unit which is designated to decompose water molecules into hydrogen and oxygen gas. It consists of a pair of nickel electrodes separated by a porous diaphragm and immersed in 30 to 35% by weight of potassium hydroxide solutions as the liquid electrolyte. The electrolyzer requires electricity with the several specifications as an input to operate and produce 100,000 tons of hydrogen annually, which are current with 2.42 times 10 to the power of 7 ampere and a voltage of 26.74 volt. In the electrolyzer, electrical energy is being converted into chemical energy. Our main process is water electrolysis, where it consists of three reactions. The first one is water dissociation reactions. The reactions can be triggered by either an external heat source or an electricity source. This is followed by oxidation reactions at the anodes. Once the hydroxide ions are attracted to the anodes, they undergo oxidations by giving off electrons, which will then flow towards the cathode through the wire, thereby releasing oxygen gas at the anode. Lastly, hydrogen ions receive electrons at the cathode donated by hydroxide ions to form hydrogen gas. Moving on to the main reactions known as the water decomposition reactions. By combining all the three reactions as mentioned in the previous slide, it is found that for every 1 mole of water molecule undergoes decomposition reactions, 2 moles of hydrogen and 1 mole of oxygen will be formed.
Now I will be presenting the list of equipments and instruments that we will be using in this green hydrogen production. Firstly, we have 4 equipments that have been used in our green hydrogen production via electrolysis process, mainly pump, heat exchanger, separators, and electrolyzer. The pump is used to pump the water supply and increase the pressure of water supply from 1 bar to 7 bar as according to the journal found. The pump efficiency would be 70% and has specified in S1 Plus according to the journal, and its electricity usage was 22.72 kilowatt calculated from S1. This is the visual version of pump we use for our process flow diagram PFD, while this is the S1 Plus model for pump 101. Next is heat exchanger, which is heater, where we heat the water supply from 25 degrees Celsius to 75 degrees Celsius with heat duty of 19275 x 7.9 kilojoule per hour calculated from S1. Next is electrolyzer, which is our main and major unit where the electrolysis of water is occurred. The anode come out will be the oxygen gas, and with oxidation process, while cathode is the place where hydrogen gas will be accumulated. All the information here is found from journal as specified in S1 Plus according to the journal. Assume no pressure drop in anode to cathode, where the heat duty calculated from S1 Plus is this much, which indicate the negative value and is exothermic reaction. Lastly is the separator, which separate the oxygen and hydrogen gas. They had 2 separators built in S1 Plus module electrolyzer model. Hence, we cannot see the stream result from here because it is built in S1 Plus. So we had extract it out from process flow diagram as shown in here. So all the information and specification are extract from the journal. During our green hydrogen production process, we have been put a control valve. The instruments, they will be have an instrument which is control valve in our process flow diagram during the process, which to control the water flow rate before going into the pump. Although we just have these one instruments in our process flow diagram, but according to ChatGPT, instruments on the other hand are used for measuring, monitoring, and controlling the parameters such as pressure gauge, thermometers, flow meters, and pH meters. So we didn't account for the PNID. If we have the PNID, we might have the flow meters, flow controller to monitoring, measuring, or recording the rate of flow, and orifice or thermostat or temperature controller. Sensor for temperature allows for the ambient temperature to influence the temperature sensors reading, ensuring accurate measurements. That's all from me. Thank you.
In conclusion, the production of 100,000 tons of green hydrogen per year can be achieved with the implementation of electrolysis process associated with water decomposition reactions in an electrolyzer, provided that the water is fed to the system at a rate of 92,486 kg per hour. Such a way to produce hydrogen is proven environmentally friendly as zero carbon emissions is accomplished, thereby saving our planet from pollution.
These are the references that we have been referred to during we doing our green hydrogen production project, that is this project.
So that's all from our group. Thank you.